Okay, my outstanding friends, this is going to be a fabulous day. I woke up in a good mood, and we're going to talk about electron flood theory, which replaces the Bohr model of the atomic structure. And electron flood theory just says that there's nothing that exists except electrons. And they are not only an electron is a negative portion, it has a positive portion, but it's dark. We've never seen it before. They call them muons. Two of these back to back make a photon, just like little bar magnets, and this is exactly what they are. And a bunch of these together make a proton. A proton is not one big positive. It's 1,839 of these electrons. And the dark parts go to the center, so we've only ever seen the glowy parts that radiate back to us. 1,840 of these electrons would make a neutron because it becomes neutral. At 1839, it wants one more particle. It's a charged particle. Now, that's a proton. Now, this is Perimeter Institute for Theoretical Physics, and what they're saying here turns me on, so I hope it's true. They're saying just one breakthrough in theoretical physics can change the world. True, and there it is right there. Perimeter Institute was created to accelerate breakthrough in our understanding of the universe. The science is complex, but the basic perimeter equation is simple. Just thinking, bright minds, illuminating ideas, brilliant future, step inside the perimeter. So let's step into the perimeter. Okay, they're going to be talking about the Large Hadron Collider, and all they're doing is trying to get the tiniest bits of particles that exist, which basically is light, and then even below that is electrons, and even below that is what an electron is made out of, which is two particles. This is light accelerating, this is light literally dividing, and this is the particle of light right here, which is back-to-back photons, back-to-back electrons. That's an electron, that's an electron. Two bar magnets. And when they concuss at the venturi, up here, they literally divide from the black from the white. The white is the electron showers. This is what CERN wants to see. And this is what we have. And just as she said, one breakthrough can change everything. There's the black particles, there's the white showers. CERN is looking for that, and they call those, here it is right here, they call those muon neutrinos turning into muons, which do not change. The black ball stays the black ball, and the electron neutrino is the white ball, and it turns into the electron showers. And that's exactly what they want to see, and that is exactly what we just demonstrated. So, knowing this, we need to engage. So let's go forward because I have a lot to speak about. They're doing a fabulous presentation. I like the people seem very nice. I'm hoping we can get some kind of interaction. Okay, so let's engage. I'm just going to talk back to what they have to say in relation to what I have to say about beyond the atom, remodeling particle physics. Everybody understands this. Everything's wrong. I mean, even CERN and everybody I've communicated with, they don't disagree. They just have nothing to replace it with, and I do. It's electron flood theory. But let's listen to this fabulous young lady speak. Here she goes.
The Large Hadron Collider, or LHC for short, is one of the largest machines ever built. Thousands of scientists and engineers involved, billions of dollars. When it's running, it can use as much power as a good-sized city. What it does is accelerate particles called protons to very nearly the speed of light, around a 27-kilometer underground loop. Well, actually, there are two beams of protons racing in opposite directions that can be brought together so they can collide. Now, everyone loves smashing things together, but with all the time and effort that has gone into the LHC, there must be a really good reason for building a machine that does that. And there is. It just takes a while to explain. But if you can understand the reason for building this giant machine, there's a very good chance you'll come to understand something quite profound about this. The everyday world. More to the point, you'll understand something about the bits that make up the everyday world and how those bits stick together. And by everyday world, I mean not only what you can see out there, but the entire universe. And not only the universe at this moment, but right back to the beginning of time. So, it's a big job. Mainly the job of these people, particle physicists. There they are, in their natural habitat.
You see this little doodle here? This is exactly what we did. We brought photons together, crashed them, and created the muons and the electron showers.
The things they're trying to discover and understand, the particles that make up our universe, are at least as small compared to the Large Hadron Collider as the LHC is compared to our entire Milky Way galaxy.
That's the particles that I am showing, and these cell phones can see them, but they're seeing them luminesce, they're seeing them radiate, they're seeing intense radiation. It's just like if you took a nuclear bomb and you put it 2 miles away from you, and it wasn't exploded, it was just sitting there. You couldn't see it. But when it went off, you couldn't miss it. That's what happens with the collision of the photons. I could show that the light coming through, all it does is sort of glow a little bit, but when it hits, boom, it's all over. And that's what we did with the cell phones. And the new applications they have, the things that we are seeing are just absolutely stunning. Anyway, this is mind-numbingly small, the particles that we are seeing. They are. I agree with that. So I understand why people were skeptical as to how we could possibly see these. But if you understand CMOS, this CMOS is the size of the particle in the CMOS is no bigger than the particle that's hitting it. And it is radiating whatever hits it as an impulse into the chip. And then the chip not magnifies it, but it illuminates an area, whatever was turned on. That's how CMOS just turns it on.
That is mind-numbingly small. So small, it's incredible that we can know anything about these particles. But we do know things. Through a process of experimentation and making theoretical models, physicists discover what kinds of particles exist and how they interact. It's a journey that never stops. Discoveries revise models, and those models suggest new experiments. When you're a kid, you learn that the world is made up of atoms. An atom is a kind of particle, a basic piece of matter, and you're told to picture them as round balls. Later, you learn that there are over 100 different kinds of atoms that can be organized into a periodic table of elements. But it turns out that atoms aren't the very basic bits that make up everything. Way back when, experiments showed that there were particles called electrons inside the atom. And if electrons are one part, what is the rest of an atom? And how did those two parts fit together? Coming up with an answer to that question meant creating a model.
That's exactly what I have, is a model, and that model is Electron Flood model. Now she shook the nucleus, or she shook the atom, and away fall of a couple little extra electrons. So she said, what's the rest of it made of? And they would always say it's made of a nucleus, which is a big proton. And then they said, well, it's not really a big proton, it's made of quarks. And then they say, well, there's more than just the quarks. There must be some muons and electron showers or something is coming out of these particles. They just don't know what to think at this point, because they collided these protons. And not only did they collide protons, which are gigantic compared to what we're using light. They used 100 billion of them, so they're digging through all this mess. We used almost nothing, so we can see everything. Now, my model says this is what a nucleus looks like, just like that. It's all covered with electrons. And then there's more electrons, which are exactly like those, only they're little magnetic particles. They have a positive and a negative. Only if there's enough of them here to make a stable, what they call resonance frequency particle, it will keep this away. This will not be allowed to come into it. But if this is polarized to want to accept an electron, it won't just accept it in its orbit, it'll accept it in its nucleus. And that's what all of the different isotopes and so forth are made out of. When they talk about nuclear decay and nuclear stability, all that is you have extra electrons or not enough electrons in the nucleus. The nucleus there's a certain number of electrons that makes it exactly stable. If you're over the number of electrons in the nucleus, it's not stable. If you're under the number, it's not stable. Then they call that half-life. It'll only stay there for just a certain amount of time. Some of them are fairly stable. They'll stay for long periods of time. Some of them instantaneously, they can't live without that extra electron. Boop, it's got to come back. Or it can't take it, and it's got to shoot away. All right, so this is what the building blocks are of atoms. They are electrons. An electron has two poles, has a dark side and a white side. As I showed, I believe I showed you that stuff. No, let's just keep going here.
When you talk about building a model, it's something that physicists have been doing for hundreds of years. One observes the world, makes measurements, then tries to find a pattern in them, and a mathematical description, a picture of what's going on that can explain those results and be used to derive predictions for other scenarios that one can test.
What scientists came up with was this: a raisin bun. The raisin bits were the negative electrons, and the bun was the positive part that balanced out the negative charge of the electrons, so the whole atom was neutral. Not a bad idea for what was known at the time, but you'll notice that we don't picture atoms as raisin buns these days, and you can thank this guy for that. The raisin bun model of the atom was exactly what Ernest Rutherford was testing when he devised a very clever experiment that produced one of the great breakthroughs of particle physics. Here's what he did. Rutherford started with some radioactive material that he knew emitted particles with a positive charge called alpha particles. Next, he chose a target,
All right, so why is it radioactive emitting positive particles? Because there's radioactive emitting negative particles too. So these are alpha particles. The beta particles are the negative particles. All right, just so you understand, there's alpha particles, which are big, huge things compared to what we're talking about, which are electrons. So we're talking about electron particles being emitted when we crashed the light. They're talking about protons hitting other protons, spitting out partial nucleuses. Okay, the difference in alpha decay versus the beta decay is that they're using huge protons, smashing them together, and then emitting a chunk which equals a helium nucleus. So in other words, alpha decay type of radioactive decay in which an atomic nucleus emits an alpha particle. So however big that nucleus was, I don't know, but it emits a chunk of itself which is equal to a helium nucleus. So that goes thrown out of there and thereby transforms or decays into a different atomic nucleus. So whatever that started with, it threw away this little four-banger out of there. So the mass number is reduced by 4 and atomic number is reduced by 2, because they're saying there's 2 neutrons and 2 protons. Well, I can't speak for that. If that's good, that's fine. But we're dealing with light. We're not dealing with these. That thing there is 1840 times 4. That's almost like it's 7,000. I think it was 7,352, something like that. It's huge compared to what we're using. We're using 1. Okay, I don't know if I show you this, but that's where they're bouncing straight back to here. And all it is impacting, and an electron will go flying off the back. And that's what they're picking up here, is the actual push to shove of an electron. It's called the Casimir effect, and they'll come flying right off of there. It will add to the other side, and one of them will go popping off of there, just like you hit it with a cue ball and drove the thing here. And if you hit it off to the side, it might go this way or that way. It's not much of a difference between pool and atomic physics. Okay, so let's just keep going here.
So if you take an object and you know its energy, and it's basically moving at the speed of light, and it bounces back, you can get a classical estimate for how much force that atom would have to apply. And if the length scale of that energy transfer is much, much, much smaller than the atom itself, that's where you say, aha, the atom is not some billiard ball, it's got to have some structure in there that's much smaller than the atom. That's how he arrived at his model, that there's got to be some solid core that's much smaller.
In time, the nucleus itself was shown to be made up of smaller particles called neutrons and protons. In effect, this model reduced the collection of around 100 elements to a more fundamental model of just 3 particles. It's easy to overlook just what a breakthrough Rutherford made with this experiment.
Now, just so you understand, the 3 particles they're talking about, an electron is the base of everything. However, when you take 1,839 electrons, you make a proton. When you take 1,840 electrons, you have a neutron. And there's a certain hum to everything. And at that certain hum, boom, they lock in and become stable. And those are the quantities, 1,839 and 1,840. And I can show you that in salt table experiments. If you look it up, they vibrate a salt table, and the higher they vibrate, the more the complexity of the design, and it all goes into the rule of 8. It looks almost identical to what I would expect an atom to look like. Okay, just so you understand, this is brush pulp. This is salt, NaCl. Both sides of the periodic chart, NaCl. That means it's basically a magnetized part, well, not magnetic, but it's a polar molecule, let's put it that way, NaCl. She's spreading all of these down just like they were electrons. And when they shake against the electrons that are on this plate, which has nothing more than the same kind of electrons, they turn into patterns at exact certain frequencies. All right, and they're starting off at very low frequencies, 458 hertz. That's 458 shakes per second. And here's what's going to happen. You will see basically hydrogen will show up. And don't forget, this is brush pup, really good guys. Now, you're going to see what I would consider to be what a hydrogen will look like. You see, there's all our electrons. It only has one center, and here's the possible places an extra electron could go. Now we go up into the rule of 8. We change the frequency up, and now we have the rule of 8, which centers the nucleus. And then it goes up and up and up until, and we keep seeing this rule of 8 pattern. If you know how to look for it, you can see it. You can find it virtually everywhere. And it just keeps getting more and more complex until you get out here where it's extremely complex. So I'll leave it at that for this. But that's why everything's based on resonance frequencies. I can't figure out myself why these frequencies exist, but they do. Now, don't get me wrong. I understand once they're set up, when you bang them, what they will do and what frequencies they will accept and give off once they're set up as that molecule and that element. But how did it get to become that element in the first place? I know they lock in at these certain frequencies, and then once they're stuck there, they appear to be stuck there. Now, I'm sure you can shake some electrons off and bring it down to, well, I know you can because of nuclear decay. You can decay from heavier metals down to lesser heavier metals. There's no question that you can shake off some of the particles. How did they get so stable in the first place? That's my, and I think I do have an understanding of it, but it's going to be extremely hard for people to accept. It's based on bacteria. Okay, so back to the gold foil experiment.
The gold foil. He encircled the whole thing in a chemical screen that would create flashes when struck by the alpha particles.
All right, flashes being struck by the alpha particle, I think they would be struck any high-speed particle, yes. And they're going to be smashing extreme amounts of energy into this gold foil, and it's going to push an electron out. All they're looking for is electrons, because that's the only thing that really has any interaction. The dark particles that I showed have no effect whatsoever other than gravity. They don't concuss, they don't absorb, they don't emit. They don't react in any other way other than to attract the white particles. So what they're going to find is these flashes, and it says almost every one of them came through. Yes, well, because every one of them is smashing against that, and that makes a reaction which drives it here. Some of them will go to the sides, yes, because if they don't hit them in a certain way, you know, they could tumble, let's put it that way. Just watch.
This is what he observed. Almost all the particles flew right through the gold foil and struck the screen on the opposite side. A small percentage were deflected a little to one side or the other.
Sure.
But the biggest surprise was when a very few deflected backwards, as though they hit something very hard and immovable. Now the
All right, so they're flashing back and hitting back here. Well, why would that happen? Exactly, they're hitting something basically immovable, but it's not. They're not driving these nuclear bits back. They're driving electrons back, flashes, just like they're hitting here. So it's an extreme bounce, basically. It's probably a little more involved than that. Because I would expect more of them to be bouncing back than just one every here and there. So that's kind of an interesting thing we'll have to think about.
The raisin bun model of the atom would not have predicted that last result. But what model does?
So if you take an object and you know its energy, and it's basically moving at the speed of light, and it bounces back, you can get a classical estimate for how much force that atom would have to apply. And if the length scale of that energy transfer is much, much, much smaller than the atom itself, that's where you say, aha, the atom is not some billiard ball, it's got to have some structure.
Okay, there you go. They're detecting a particle that is much, much, much smaller than the particle they emitted. So that's the key. Let's listen to that again. The little details are the thing. He says you can get a classical estimate for how much force was required. Now listen, so he's saying you're only getting a little tiny bit back. Well, he's getting an electron back from smashing it with a nucleus.
Classical estimate for how much force that atom would have to apply. And if the length scale of that energy transfer is much, much, much smaller than the atom itself.
All right, the length scale of the transfer, so it's transferring back a very, very, very small particle.
That's where you say, aha, the atom is not some billiard ball, it's got to have some structure in there that's much smaller than the atom. That's how he arrived at his model, that there's got to be some solid core that's much smaller.
Yeah, the electron.
In time, the nucleus itself was shown to be made up of smaller particles called neutrons and protons. In effect, this model reduced the collection of around 100 elements to a more fundamental model of just 3 particles. It's easy to overlook just what a breakthrough Rutherford made with this experiment. Not just for what it discovered, but for the technique of colliding particles together as a way to penetrate inside the structure of matter. Before we move on, we need to get a few physics concepts straight. When you throw a ball into the air, the ball is interacting with Earth's gravitational field. As the ball rises, we see it slow down as the gravitational field exerts a force on the ball. A physicist pictures this as the energy stored in the motion of the ball moving into the field and then back into motion as the ball falls back down. In Rutherford's experiment, the alpha particle and the gold nucleus were interacting in the electric field surrounding the gold nucleus. As the alpha particle moved directly towards the gold nucleus, it began to slow in the field. Its energy, stored in motion, moved into the electric field and then back into motion as the particle flew off in the opposite direction.
All right, the reason for that is every single particle is made up of electrons. So there is electrons with a field surrounding this. This one has a field surrounding it. When those fields collide, they push apart. It's called the Casimir effect. You look it up. At very close atomic distances, every single particle there is will push every other particle apart. Magnetic, non-magnetic, doesn't make any difference, because every single particle there is coated with the white portion of the electrons, which is the pushy part. The black portion of the electrons goes into the center. The center will be where the dark portion is, and you will never see that because it will still be coated like white particles here. They'll be coated everywhere around it. But the dark particles have no problem being on top of each other. They will migrate to the center. All right, and that is dark energy. It's gravity, and that's what causes gravity. The Earth has a ton of extra dark energy in it, which is the gravitational portion, which pulls anything with electrons, and everything has electrons. Okay, it's basically nothing more than taking two bar magnets and pushing them towards each other. One will oppose the other. Now, these are the same size, but if you had a tiny one hitting it and bouncing back, you'd see a tiny particle coming back. You know, they're saying that, for some reason, you're getting a tiny particle coming back because of some other reason, but it's because it's an electron in my world. That's why. All right, so let's just continue on. She's talking about the gold nucleus being smacked by
Gold nucleus. As the alpha particle moved directly toward...
Now, don't forget, the alpha particle, to me, is a gigantically huge particle, and it's coming towards the gold nucleus, and it's going to bounce back. But it's not, to me, what she's getting back is an electron, not a nucleus.
towards the gold nucleus, it began to slow in the field. Its energy, stored in motion, moved into the electric field and then back into motion as the particle flew off in the opposite direction.
Yes, because it's an electron that doesn't want any more electrons in a nucleus. It says, no, you can't come in here, get out. And it pushes it away. That's what's called light. It's radiation. It's push to shove.
In a particle collision, the more kinetic energy particles start out with, the closer together the particles will get. The history of particle collider experiments is one of designing larger and larger machines to create higher and higher energy collisions in order to see deeper and deeper into matter.
Now, my question is, if we started with light and then we can see the particles, which I showed, is that better than starting with gigantic things and digging through the debris to try to find the particles that are the smallest particles? And even we found something that's a little even stranger than that. But let's listen to what they have to say. But I believe that starting with light is a better option than starting with gigantic particles.
As particle accelerators became capable of focusing energy in such a microscopic volume of space, something quite extraordinary happened. New particles were created. I know, that may sound like magic, but at the scale of fundamental particles, the rules of physics not only allow for it, they predict that it will happen.
They weren't created, they were just observed, because then you come into the bosons and the muons and all of these little Higgs fields and so forth. They can see them. They just don't know how they occurred. And the bosons and the muons are dark matter. Nobody's ever seen it before because it's always been attached to the white matter, and the only thing that radiates is the white portion, so nobody's ever seen it.
The key rule is E equals mc squared. And what that means is that mass and energy can be converted one into the other, just like you can convert British pounds into dollars at a certain exchange rate. Only the exchange rate between energy and mass is c squared.
No, that's just incorrect. C squared has nothing to do with it. That's the speed of light, and the light speed can change. I've shown that. I showed light accelerate. If you can accelerate the light, the c squared really doesn't have anything to do as a fixture. You might want to use it at some point, but it's not a fixture in the equation. Energy equals mass. Yes, absolutely. Well, what does mass equal? Mass has a lot of factors. It's not just the weight of the particle. It's the speed of the particle. It's what it impacts with. Because the mass is what it bounces back with, is what I'm going to call the energy. Energy is impact value. Let's put it that way. and I showed our energy, the impact value is, I think, 200 times the input value. Okay, now don't forget, we're working with light. Light is entirely different than protons. Protons are 1,839 electrons. Light is 2 electrons back to back, as I showed. And the electron consists of a dark portion and a white portion. We've never seen a dark before because it just doesn't show up. And we can't see it either until we put it through the Venturi. When it hits the Venturi, that's when it shows up right here. Now, prior to that, it's just a wave of light coming through. Now, this has captured the initial input of the wave, concussing all the other fields in front, because every single electron and every single thing there is, all gases are made of electrons, just like everything is. Everything's made of electrons. So oxygen and nitrogen and everything there is in the air, smoke and the whole 9 yards, are made of electrons. When they concuss with a field, they glow. That's what this glowy little stuff is here. It's not just nothing. It's because this is concussing everything that's in front. And that's as fast as this wave would go. That's what they consider the speed of light. Well, there's a particle in there. As I showed the particle, there it is right there. So just assume, or think of it this way. Don't assume anything. But think of it this way. This is that particle. And everything in front of it, because it has a field in front. It has a magnetic field, huge field, huge. Look up the 21 centimeter line for hydrogen. It's absolutely amazing how big the field is, 21 centimeters. So everything that's within its range coming forward has to concuss, because this is a field. It's not the particle. That particle actually may be way back here. I don't know. But I would assume it's in the front of the wave. I don't know. But I can tell you what, it left the wave right there as it accelerated. And anybody that can't see that, I don't know how they can miss this. It's obviously something has left that wave and pulled out of the field that it was in. And there it is right there. And what happened here, it concussed, and the energy value here, this white spray is, they say 200 times more energetic as what it would be here, if this is the particle that I am claiming it to be, which is electron showers and muons. If that's correct, this is an increase in energetic value of 200 times, which means that that could possibly, and I'm just talking possibly, lead to some free energy. Now, let's just look real quickly at the rest of this. This is the Higgs fields that come at us if we were looking at this way. And so we're looking down into the Venturi, and these are the fields as the white spray gives it up and smashes into particles, then you get this effect over here, and I'll show you up close. This is a very, very strange one. This particle here appeared to come in backwards, I believe. So they normally spin to the right. I believe this was a left-hand spinner. And it hit another Higgs field, and then that happened. So there's a lot to look at. It's kind of fun. So if what I'm showing is correct, and I don't see how you can miss that that is accelerating, so that is light accelerating. That is not allowed for Einstein, so I'm not thinking Einstein's right on this 100%. And in addition to that, this is a particle, which I showed the particle, and it concussed, and it actually divided. And when it did, it created the white showers and the muons. So, and which are particles. And even today, Fermilab, Don Lincoln at Fermilab refuses to even talk to me about this. I tried over and over and over to get him to look at this. Finally blocked me, and he doesn't want to. He says, I have no interest in it whatsoever. I said, we're accelerating light. Maybe we can use it for free energy. I'm not interested. You know, he's running a government program at Fermilab. That's not right. But anyway, that's a whole other issue. Hopefully somebody will take a notice of this and we can get something done. Because if this is correct, we could get some free energy out of there. I don't see how we can miss with this. It doesn't take a whole lot of energy to make this laser. And then if you can increase it, well, increase is an increase. So the more lasers you add, the more increase you're going to have. And it's not expensive equipment either. This is very, very, interesting to think that there may even be portable handheld devices that you can carry around that do this just like your cell phone does and creates high energy, and you just plug into it and you got it. Because all you need is a couple of little devices within the absorber, and you'd have to absorb it right in here. Here, let me just show you what happens at the Venturi. All right, there you go. I probably showed you this about 20 times already, but I don't care. There's the black balls that's separated from the white showers. It's just what it is. And again, I'm sure I showed you this one too, but I want to make sure you understand. This is not silly. This is not a joke. This is what they want for the muon neutrino, the black ball to stay the black ball. They want the electron neutrino, the white ball, to turn into a shower. That's exactly what I'm showing. And I think Fermilab should reconsider and look at this. This is very important. And it's not just silly. I'm not a tinfoil hat guy like Don Lincoln called me. It's very hard to engage with these guys once they get into these positions of power. They don't want to be, they just don't want to engage. Let me put it that way. I don't know what's going on with him. But we had a row, let's put it that way. And I'm blocked now. So if anybody can do anything about this, if we get free energy right in here. And all you need right here is what would be transition metal thin film substrate. And why would it have to be transition metals, thin film, CMOS, that type of stuff? Because they have the deep ability to absorb electrons in the lower energy levels, and that allows them to flow all of the types of energy coming through and absorb it, I believe. Now that's just what I'm thinking, but if you look up, well, I'll just show you quickly. All right, these are the transition metals. They're talking about aqueous solution. Well, you don't need an aqueous solution if you have thin film and one layer over the next layer over the next layer over the next layer in depths of who will absorb how many electrons. And these are all the states of oxidation that these things can have. So they can absorb all these different frequencies of light, basically. And you may have to put them in depths that will allow the frequency to be absorbed correctly. But you may have to have several layers of these. I don't know. That's for an engineer. But I can tell you what, this is what you need to do to absorb it. This is just like the CMOS stuff. It's all transition metal based. All right, this is probably what you have to dope something in there so that it acts more like a conductor than a semiconductor. Really what we want is an absorber, to have all of those extra energy levels to be filled and then pushed down. And you may need a Van de Graaff generator, a little tiny one, or even a Tesla coil to create a whole lot of extra electrons. And maybe even a frequency modulator to sort of push them into the right range of acceptance, let's put it that way. Because these are going to be different frequencies, which means light spins. This is a light particle. In my world, this is how light works. It spins. And I can show this. I've shown it a million times. Now, what does that mean to the semiconductor when it hits it? If it's spinning real fast, it might just get by it. So you may have to have it deeper inside there, something to slow that down a little bit, and where it can be picked up. But that's what doping's all about. It's an extrinsic additive to the semiconductor. Usually they use silicates. Everything is basically silicon based. That's why they call them silicon chips. Well, they dope them, basically is how that works. All right, so what you want to be doing is doping pure silicon with this group 5 elements such as phosphorus, extra valence electrons, are added that become unbonded from individual atoms, allow the compound to be an electrically conductive N-type semiconductor. Now, there's people that know how to do this stuff. It's been a long time since I've done this, but silicon is basically your substrate, and then you either film dope it or you heavily dope it, or now they're using thin film transition metals, I believe. And again, I'm sort of out of the loop of this, but I do understand the light and so forth. I understand this stuff pretty good, and the reason this is silicon and carbon basically almost the same. Only silicon is a more dense molecule than a carbon. Carbon has 4, and silicon has 4 in the valence shells. That makes them bond in interesting ways. And doping means you put these little particles in the middle of them, and they can do a whole bunch of special things and push electrons or absorb electrons. All right, so if Einstein is wrong, and which he is, speed of light really has nothing to do with it. It's squared. Anyway, here goes.
The speed of light squared.
Mass and energy are just two faces of the same thing. You
She's
cannot
right, exactly.
differentiate between one versus the other one.
One way to interpret this formula is to think of mass as just a type of energy. And consequently, if you have a lot of energy, you can also create mass, or in other words, matter.
You can actually see particles popping into existence in the particle detector of an accelerator. For instance, in this image from a bubble chamber detector, the tracks were created by charged particles passing through the detector. The detector has a magnetic field, so particles curve one way or the other, depending on whether they have a positive or a negative charge. Look closely at these two spiral tracks that appear out of nowhere and curve off in opposite directions. What you can't see is the photon, a packet of energy that was traveling through the bubble chamber when it suddenly turned into these two new particles. This
It's exactly what I show. These are the bright one and the dark one. So these are the things that they're seeing, and they don't realize it came from nowhere. It didn't come from nowhere. It came from a collision of basically particles crashing into each other. And we forced them to do that with our Venturi. But this is like an accidental result. And they have seen this at CERN. They know all about this. They say that the two protons come so close to each other that they create new material. They don't create anything new. They push out electrons, and they push them out a dark portion and a bright portion. Exactly what I showed.
This track curving to the left is an electron which has a negative charge. But this track curving the opposite way has a positive charge and turns out to be the antiparticle of the electron called a positron. An antiparticle that has the same mass but the opposite charge.
And so when you collide things with lots of energy, what typically happens is that there's lots of particles there, and they will be pair producing new kinds of particles all the time, particles and antiparticles, as long as you have enough energy to produce their mass, which is related to energy through E equals mc squared. In all these collisions, the things that are coming out were not there to start with, and so you're getting a...
Well, they are there to start with, but they're in their attached form. When you smash them so violently, you've just broken them into little bits and pieces, which is the positive and negative portions of the electrons. And the dark matter is the one that you guys are looking at to spin backwards. Now, I can't see them spinning. I can see the particles. I can see them trying to find the white particles again, but I can't see them spinning. So let's see what you have to say here.
Sampling of all possible particles that could be produced at the energies that you have access to, which makes it much more efficient. You have to choose the initial thing carefully to have the right ingredients. You can collide almost anything at high enough energies, and you're going to get everything out.
Exactly, and so they just digging through the debris. Now, we started with light particles, so we don't have to guess what these things are. We can see that the two particles were the bright and the dark, and they separated, and then they came back together basically instantaneously, because the black is gravity.
So how much energy do you need to create a particle? About this much. Not much. But it's not only a matter of how much energy you create, but how much energy you can put into a very, very tiny space. In fact, when particle accelerators began operating at high enough energies, all kinds of new particles began showing up in detectors. These weren't the particles that make up the matter around us. Instead, they were massive particles that would pop into existence and then decay quickly. In a few decades, physics had gone from 3 fundamental particles found in the atom to a multitude. They called it the particle zoo, and physicists had to find a model that explained it.
So in
The model that does explain it is that there is nothing but electrons. All right? There's nothing that exists that is not made of those. And they are so small that it takes 1,839 of them to make 1 proton. So that is, the Bohr model is no longer, and they know it's not good anyway. So he's going back to the 50s and 60s. Let's go back, here goes.
In the 50s and the 60s, particle physicists were discovering new particles at a very fast rate. And it was very unclear whether or not there was some underlying organizing principle sort of tying together all of these particles, or if each new particle is just sort of a separate entity with its own properties sort of unrelated to the rest of the particles.
When physicists develop a model, they're finding a pattern that explains what they are seeing in their experiments. In the everyday world, we're pretty good at detecting patterns, but some patterns are more complex than others. Here's what I mean. You know those music visualizers that you can find on digital music players? The ones that use information from the song you're playing to alter and transform the animation. The result is a complex animation, but rhythmic and beautiful. Now, imagine that you lived in a world of music visualizers, but you couldn't hear the music. As beautiful as it seemed, it would be difficult to understand why your world looked the way it did. But if you were the curious sort, you could, by careful observation, start to find patterns in what you see. And with some creative thinking, you could even reconstruct the underlying music. And with some clever modeling, you'd discover little things called notes, which combine in different ways to create your world. The particle zoo presented a similar problem. What was the pattern that connected these particles together?
All right, I can tell you why you have a particle zoo. Is because instead of starting with what we were starting with was these particles, which when they broke, there was only a couple of particles. They started with hundreds of billions, literally hundreds of billions of particles, and then they'd have a chunk like this, and they'd have another chunk like that, and they'd have some more like this, and they'd have all kinds of different things coming down. But then they would get to the very tiniest bits, and they would see these little things, and this is where they ended up getting down to the neutrinos.
Physicists did eventually discover a pattern by arranging groups of particles according to certain characteristics. The pattern revealed that most of these particles weren't fundamental at all. They were made out of a combination of more fundamental particles called quarks. There are 6 quarks in all, 12 if you include their antiparticles. The up and down quarks are particularly important for us because they make up the protons and neutrons that we find in the everyday world. Each proton or neutron is a bundle of 3 quarks. 2 up quarks and a down quark make a proton. 2 downs and an up make a neutron. While quarks seem to solve the problem with the particle zoo, they left physicists with a new one. How do these quarks stick together in the way that they do? The answer required coming up with a new fundamental force of nature called the strong force.
The strong force is dark matter. Dark matter is the dark balls, they are so attractive that they pull back the white particles instantaneously.
The strong force is a fundamental force like the electromagnetic force, but it acts very differently. A quark can have one of three charges, which are labeled as the colors red, green, and blue. Combine them together, and you get a color-neutral particle. And while the electromagnetic force...
I just want to tell you why you get these different three colors is because of the speed of the spin. Literally, that's what it is. Blue, you're going to be spinning like... It's a spin. These spin. So you're going to be spinning at this fast. If you're red, you're way out here. If you're green, you're somewhere in the middle. That's the difference in the colors of the re-radiated particles. And the reason is because there are different distances that electrons will have attachments to their nucleus. And if you pull one from the very close part of the nucleus, it's going to be, you're going to really have to pull it. It's going to shoot off like a rocket. That's your blue. If the red is way out here, you're just going to knock it out of there and it's going to sort of roll away. And the green is going to be in the middle. So that's what she's talking about here. Now I know this is going to get very long, but it's a kind of complicated deal.
Force gets weaker the farther you get from a charge. The strong force is weaker nearest the particle and actually gets stronger as you move away. Now,
That's not true.
think about that for a moment. As long as the quarks are near each other, they're bound together loosely. But the moment they try to separate, they experience a stronger and stronger force that keeps them confined. A bit...
All right, I agree with that because the binding force of the black and the white is just absolutely enormous. And they come back instantaneously. Let's just look at that first. First of all, I just want to show you. This is how light spins. It spins this way. Sometimes it goes off to that side. Sometimes it spins off to this side. There are all these little particles come flying down in the spin like this. This is literally a drill bit. It's a right-hand spin. And these are repulsion patterns. They're not overlapping. This is a single slit. All these particles do not want to be next to each other. The white will push the whites away. They just don't want to be near each other. The black couldn't care less. They'll attach to anything and they suck the particles back instantly and violently. And you can see it when they come through the venturi. And here they are approaching the venturi. The black is apparently too dense or something. It will not crush like the white. It crushes down and squirts its way through. The black just is like a bowling ball, and it won't get through. It can't go through. I don't know why, but it goes around and it comes back. And I say that's dark energy and dark matter, and we never knew it was there because you never would see it come apart from the white. The white is the only thing we ever see, but just because of the way it approaches the venturi, we could see they were attached, then they came apart. And that, again, I'm just going to show you, be sure we don't miss a damn thing. Coming in, there is no definition to them. Before they start to hit here, you don't even see them. And then they start to look like a little Oreo cookie, and then it does this, it turns into a little box. And then and then it spikes up here and starts to glow. And the more they glow, and then they impact here and they fall apart in little bits and pieces. And that's when you get the electron showers and the muons. The muons can't get through. And the black ones, they are nothing but attraction. So it's gravity, it's dark matter, dark energy, the strong force, the whole 9 yards is that. The white ones, they radiate, we see them, everything's fine with that. All right, so I just showed you. They don't want to come apart. The black one just really wants to lock everything together. So she's saying when they concuss and they start to divide, it says it's a bit like an elastic leash that pulls everybody back together. And I agree with that. But it's the black one that does that.
Like an elastic leash that pulls back the further out you pull it. That makes it nearly impossible to separate quarks from one another. What we call a proton or a neutron is really the very, very small area where a group of quarks is confined by the strong force. That nucleus that Rutherford discovered so long ago is actually a seething mass of quarks held together by the strong force in groups of threes, which we call protons and neutrons. And around those, held more loosely, are the clouds of electrons.
All right, so my contention is that the nucleus is made of electrons. And then there's a certain number, it's becomes stable, and it says, I don't want any more. And then more will want to come into that dark matter. It loves, it really wants to attract more electrons, but there'll be so many extra electrons in the core already that it will repel them and keep them in the cloud surrounding it. That's what quantum's all about. It says, we got plenty here, but stay out and stay out at 2 angstrom units, and then you can have some more, and they'll stay away from you by 5 angstrom units, whatever it is. And that's how you build your shells of electrons. But it's nothing but electrons. And when they radiate electrons. You can break particles, yes. You can have neutrons break, and protons break up into nuclear bits, absolutely, but they're just nothing but still chunks of electrons that are not stable. Stability comes from a certain quantity, and this is not unknown. There's an atomic number and atomic mass. All right, you see this here? You got the atomic number and atomic weight, all right, an atomic weight, call it. But the atomic number is 1 and 2 and 3 and 4 and so forth. The atomic weight is altogether different. Because you come up to helium, and instead of being just 2, it's 4.023 or 033, whatever it is. My eyes are not good. Anyway, the atomic weight is what we're dealing with. And at 1 atomic mass, I call it atomic mass, it is 1,840 electrons, or 1,839 electrons. All right? And then as you add more and more and more, like helium, hydrogen itself, I figured it out, it's 1,854 electrons, approximately. All right, so hydrogen is not 1 proton and 1 electron. It's 1,854 electrons. The mass of the center is like 1,853 or whatever electrons. And then there's 1 around surrounding, or there may be more surrounding it. Because hydrogen is not just hydrogen 1. There's hydrogen 1, hydrogen 2, hydrogen 3. And then there's all kinds of isotopes in between. There's a lot that is just fluffed over because they can't explain.
But the complete model of particle physics involves more than the atom. It has to include all particles that exist in the universe.
And now my contention is that there is nothing but electrons, so that's solved.
The current model of particle physics is called the Standard Model, and it describes all the fundamental particles that we know of and the forces that make them stick together. It's one of the most successful models ever. It can make predictions about particles to an amazing degree of accuracy.
If you take the particles that we know about, and you ask, what's the most general way in which those can interact at low energies, consistent with quantum mechanics and relativity, the Standard Model is it.
I'll describe it briefly so that we cover some of the particles I haven't mentioned so far. First, there are the particles that make up everyday matter: the electron, the neutrino, and the up and down quarks. Then there are what we call the second and third generation of these particles, more massive and unstable, but otherwise identical to their lighter cousins.
If you just keep adding the electrons together, you get all these things. But I'll let her make the points go.
In the Standard Model, there are also particles associated with each kind of force. These force particles, called bosons, carry the information of a particular force. For instance, the photon carries the information of the electromagnetic force, the gluon for the strong force, and the W and Z particles for another force called the weak force. So these are the particles that make up our universe and that have been detected in particle accelerators so far.
All right, don't forget now, the particle accelerator smashes 2 things just into debris. So these are little bits and pieces that they know they're very, very tiny, yes. And they know that they have these exact characteristics in every little chunk of these things, yes. But do they know, they're trying to get down to these, the bosons and the electrons, the muons. If they can get down to the bosons, the electrons, and the muons, then they're going to be happy. But they still haven't got there, and we did.
Now, it's one thing to make a list of particles, but a complete physics model must describe how all these things relate to one another.
For a given model meaning a description of how the world works, there are a set of equations. And things like particles and particle interactions and forces, all of these concepts are in the equations.
So, for a physicist, the model will look something more like this.
I did all this stuff. 50 years ago. And there's no way in the world you can do enough doodles to take away the fact that you cannot have a massive positive core and little negatives floating around. They would just slam together. And now that I have the evidence, which I have shown, this sort of becomes kind of silly, don't you think?
Mathematical equations that spell out how all these particles relate to one another. Now, if we look closer, we might notice a term in here. Let me find it. Here it is. An H. The H is a particle called the Higgs boson. And it took physicists decades and billions of dollars to find. So why were physicists so sure that it existed? For one thing, the standard model doesn't work without it. Imagine you're standing on a subway and it stops suddenly. Yeah, you keep moving forward. That property of matter is called inertia. Inertia is a resistance to a change in motion, and it is caused by the property of matter called mass. In fact, objects have inertia because of their mass. Most of the mass of everyday matter comes from the energy involved in holding its fundamental particles together. E equals mc squared at work again. But fundamental particles can have a mass too, all on their own. So the standard model needs to explain where fundamental particles get their mass. That is where the Higgs comes in. Here's how it works. First, the Higgs boson is associated with a field, and it's the Higgs field that is the really important idea. The Higgs field fills the entire universe. It's everywhere. You can't get away from it, like a sticky fog that has settled around everything.
All right, and I don't disagree with that. However, the field doesn't exist on its own. The field exists because the particle is there creating the field that surrounds it. Okay, so my explanation here is that everything there is has a field around it, and that's what they're talking about, these Higgs fields. Now, they don't see them until you do experiments like we did. We actually could see them because of them literally developing in space as we watched. All right, you've seen the light exploding at the Venturi. We're looking directly into the Venturi, and the light is coming at us. From here to here, the particles are those white showers. So there's nothing happens until they smack into reality out here and create the Higgs fields. And now we can actually see them. You don't see them, but they're always out here. But now they got excited. And it's basically what CERN was doing, only they were colliding gigantic things and huge fields showing up. Now, our fields are fields from the little tiny particles, the actual particles. They're not these huge balls of energy, because everything has the same signature. But when you start to get down into looking at the particles the signature that represents, then you're in the realm of where we are. Now, don't forget, some of this CMOS technology in these new smartphones is absolutely stunning. And I showed all of the light and the light accelerating, the Higgs fields. Here's the Higgs fields coming at us, and we actually created a blue from red. They started all out red, and this one got pinched on both sides, so you can actually accelerate the light or crush it or whatever. This is actually spinning light coming at us. These are the ones that are closest to us, and these are the troughs around them. And they're spinning, just like I showed you. They're spinning particles. So there's a lot to look at here. Now let's go back to the presentation. Okay, so I will agree that there are particles that are, every one of them has a field around it, which we can call a Higgs field, but you're never going to see them until they smash their particles head on. So here, let's see what else she has to say here.
Because it is everywhere, every particle is traveling through it, and most particles are interacting with it. When a particle moving in the field tries to accelerate, it experiences a resistance. The idea is that the particles don't have a mass on their own, but only through their interaction with the Higgs field. How much resistance the Higgs field exerts depends on the particle in question. If you're...
All right, let's just talk about this Higgs field. The Higgs field is the field around a magnet. It's basically a magnet, and it has a positive and negative field around it. When it flows through the air, an electron by itself is nothing more than lightning or heat or whatever. But once you attach two electrons together back to back, you have a photon. Photons bounce. Heat and electricity, they will attach to things, or they will just invade things, but they won't really become part of oh boy, this is hard to explain. Put it this way. Photons bounce. They're already complete. They have two electrons together. They bounce. Electrons want to incorporate into something. So they will burn you, or they will just click on and hold on to other molecules that will allow them to just sort of ride with them. Because electrons are nothing more than heat. They're all over the place. There's tons of extra electrons in the air. But when they hit a certain saturation point, it's a different story. That's when you get lightning. That's when you get static discharge. If you collect enough electrons on your body, you touch a water pipe, bang! That hurt. I can feel it right now. All right, so I hope that made some more sense.
If you're a particle like an electron, you interact with the Higgs field and experience a resistance every time you try to accelerate. On the other hand, if you're a photon, you glide right through the Higgs field without interacting. You're massless, and you go about your business at the speed of light. Remove the Higgs from the standard model, and it would predict that all particles would be massless particles, just like photons, which they are.
I just want to say something. She's basically right about this, that electrons are a charged particle, so they're going to interact with all the other charged particles in a more aggressive way than photons. Photons will bounce off them, but electrons will want to attach, just like I was saying. You walk through dry air and they will attach to you because you have water molecules. Photons won't attach to you. They'll bounce off of you. So let's go a little further here.
They aren't. And it's a good thing, because our world would be very different without the Higgs field.
If you look at the world around us, we know all the atoms are built out of protons and neutrons. Now, each of these protons and neutrons is itself built out of 3 quarks, but different quarks. And the Higgs field interacts with these different quarks, slightly different amounts. That actually makes the neutron a little heavier than the proton. The fact that the Higgs mechanism makes the
neutron is 1 electron heavier than the proton, because it is, instead of 1839, which is the proton, it's 1840 electrons.
Neutron a little heavier allows you to have a stable proton, stable hydrogen. The fact that it's only a small difference lets you build up the entire periodic table of elements. So that means we can have all of the materials that this chair is built of, that the world is built of, chemistry and stars. Every process that we know and love and that makes this world possible is largely due to this precise difference between the proton and neutron masses.
It's the electrons. They're all
To prove
electrons.
that the Higgs field exists, physicists would need the biggest particle accelerator ever built. Hold on. They've built one of those. Because fields are associated with force particles called bosons, if you detect a particular boson, you have evidence of that particular field. So when the Large Hadron Collider detected the Higgs boson, that was evidence that the Higgs field existed. The LHC generated collisions that involved 10 times more energy than any previous accelerator.
The LHC, the way it reaches these very, very high energies, has a number of different components to it. And the first, which many people don't think about very often, is the kind of particle that's being collided. We're colliding protons, which are 2,000 times as heavy as, for example, an electron.
We accept.
Exactly. We're using electrons. Well, it's not 2000, it's 1839 approximately, but we're using electrons, and electrons glued back together, back and forth, are like two bar magnets and make up a photon. And I could show that, and I have shown it in the light experiments. It's very, very hard to dismiss that.
Accelerate protons by passing these protons through an electric field that is being generated by accelerating cavities. It's much like a surfer that gets pushed by waves in the ocean. These protons get pushed by an electric field as they pass through these accelerating cavities. And in gaining speed, they gain a lot of kinetic energy.
It's a combination of a large size and very, very strong magnets, which you use to bend these particles in a circle to keep them under control. There are these quadrupole magnets which are used to squeeze the beam down and make it as narrow as possible, make the particles as dense as possible, so that when they collide, you have those very, very high luminosities to give you the most number of collisions.
High luminosities, exactly. And they are using the same cameras that we're using in the smartphones. They're CMOS chips. They're not a whole big difference. It said, I think I showed the article that said they're using the same CMOS technology in the Large Hadron Collider to visualize these interactions. Exactly the same thing. And they're using also the smartphones for cosmic rays, and now we have them for field effects. It's absolutely stunning.
Imagine protons as fishbowls and the quarks as ice cubes tossing around inside. And they are flying towards one another at high speed. Most of the time, the bowls would just smash together. But every so often, two of the ice cubes would also collide. In the LHC, it is the rarer collisions between quarks and the gluons that hold the quarks together that produce the really intense energy needed to create a Higgs boson. It's one thing to create a Higgs event, but you also have to be able to see it happen. No particle accelerator is complete without its detectors.
Our detector is made up of different layers of sensors. And each of these sensors is designed to measure the trajectory, the energy, and also the different types of particles that emerge from this head-on collision. We wouldn't directly see the Higgs, but rather the different types of particles coming from the disintegration of a Higgs.
And by the pattern of those particles, physicists knew a Higgs boson must have been present.
So here's the problem, though. So you have billions upon billions of particles flying into this detector every fraction of a second. Okay, and you have to
Billions and billions. We're using just light.
digitize all the information that represents their trajectories. Okay, you got to digitize all that information. You got to pump it up to computers to throw out most of it, because at a raw level you have well over terabytes per second flying up into the main processors that are actually in the collider halls, and that's got to be filtered down to a more manageable level, which you can then pump out into a computing grid to reconstruct exactly what happens in these events.
At a billion or so interactions every second, there's a lot of data to sort through. And even though physicists knew what kind of signature a Higgs event would produce in the detectors, sifting through all those events and collecting enough data to find what they were looking for took years. But when at last the discovery was announced on July 4th, 2012, all those years of effort filled in a critical part of the standard model. But the LHC is doing much more than looking for one particle. It is delving into matter at the smallest scales ever, allowing us to look into a realm of very high energies, and it is recreating conditions that haven't existed since a split second after the Big Bang. And if experience has taught us anything, it's that when you explore deeper into matter, there's a very good chance you'll discover all sorts of new things.
On what scale the LHC will be important, we don't really know yet. But what we do know is that it's answering questions that have been the driving questions of particle physics for 20 years.
What I would really love to see, and what I've been working on, is looking for substructure to quarks. So this is looking for excitations in quarks. This would be earth-shattering in the sense that it would take us to the next level. It would take us to something smaller than a quark.
Okay, my friend, you got it. Once again, please respond. This is what's smaller than quarks, and the quarks are made of the electrons, and everything is made of electrons. There's nothing other than electrons. And electrons have the dark matter side, and they have the explosive, energetic side that we've always known about.
Using techniques that were developed 100 years ago, but at much, much higher energies.
I hope that they see a candidate for dark matter, because that's one of the biggest puzzles as a cosmologist that we are facing with. What is this mysterious matter that is dominating our universe, but we don't have a clue what it is. So let's hope there is a candidate and let's we can see it. That would be a big discovery for me.
I think, and I truly believe that in 20, 30, 50 years from now, in physics textbooks, we'll be talking about the pre and post LHC era in terms of our knowledge and description of nature.
What?
I'm just going to stop it here, but do you know what they're trying to do now with the LHC? Is the exact same thing we're doing. Actually, let her finish up, and then I will make my final statement.
What I'm really curious about is how science will follow up on this experiment. How deep can you explore into the little bits that make up our everyday world? And what kind of models will come out of what is discovered? I guess what I'm saying is that even this moment in science will pass, and we will move on to new discoveries, new models of the world. And that is pretty exciting.
Okay, it is exciting, and I'm hoping somebody will look into this. So, I'm ready. Okay, here's what we did with the pulse red laser. And laser is just laser light. It's the smallest basic particles there are almost. What we did was we forced them to make their fields crush into what is a tuned venturi. And you have to tune it right, and you have to know what you're doing a little bit. But what it does is it separated the black particles from the white particles and created electron showers. Now they've done this at CERN, but just by accident, and didn't realize what they did either. Because we didn't create anything, we just separated something. By the way, this is the entire electron flood theory. All it is, everything's 100% dipoles. You have the muon, dark energy, dark matter, gravity, whatever you want to call it, and then you have the electron, which is energetic, and it pushes and shoves. A proton is 1,839 of these. A neutron is 1,840. Forget that stuff. I got to rewrite that. The electrons push, well, it's true, the M, which is the muons, attract everything else, and they do not shove at all, and they don't explode. Atoms, molecules are bigger masses of electrons. That's all they are. That's the dipole electron, and that's the photon, which is 2 electrons, and I believe it's 2. It might be 4. These are things we need to look into. All particles will have their dark matter in the center, surrounded by the white particles that radiate, that we can see, that bounce other particles off them. We've never seen the dark before. The only reason we see it now is because we separated. You never see that before. You still don't see it except for here. Anyway, it goes on. But this is my point: is we're crushing the particles into this region that they have to interact with each other in a very aggressive way. And when we did, it squirted out of here, which is the exact same Venturi effect as an old-style carburetor with gasoline. They call it atomization. And it does. It makes them atomize. And it literally is fission. It's literally atomic, photonic fission. We separated the black from the white. That's fission. Fission. Anytime you separate something from something else, it's fission. And at this point, we're at the lowest point of particles that exist that we know of. Now, I'm going to leave it with this. This is exactly what CERN is doing right now. they're trying to do what we did, but they did it by accident with protons. They smashed together just accidentally and gave off these W bosons. But they wanted to do this for, see, they're using 100 billion particles at a time. Insane. We're using 2. They wanted to do this many years ago, but since 1978 they discussed doing this, but they just didn't know how. And it's just, these collisions are very clean as we're colliding photons, elementary particles, not composite ones like protons. So they really want to do this, and I really want to help. And they're going to try to use this gigantic machine. I don't know why, because everybody now is starting to understand you can do this on a tabletop. And again, I tried to correspond with some people about it, and they're talking about doing it, but they won't respond to me. And I have some information that'll help them. So I'm hoping this place in Canada, I tried all the places in the United States, universities and so forth, and they, you know, they have their own way of doing things. They're just not interested. So these people are saying the right words. I'm hoping that's what's going to happen. They'll take an interest. All right, I love you all.